hear it, but I will replace Noel. So Noel is the man that has created the presentation. So, but he's not feeling so good today. So as he still have a lot of work this afternoon, I will replace him for these presentations. So we are going to speak about the 1MI approach, and so the idea here is really to link materials, process, and performance, but also to move progressively to a link between the real world and the virtual world in order to have a more sustainable approach of manufacturing. So inside Hexagon, you are going to find several divisions, and Hexagon Design and Engineering is part of the Manufacturing Intelligence divisions. But as you can see, Hexagon is also active in many other fields like mining, like geosystem, geo-safety infrastructure, etc., etc. But today, what we are going to speak in terms of 1MI will be really doing the focus on the manufacturing intelligence. As explained by Serge, Hexagon has already a very long history through different types of acquisitions, and the part that is very important for us is the fact that around 2017, Hexagon has acquired MSC Software, and by acquiring that, they also get an access to the different multi-physics tools that will be presented to you this afternoon, like Nastran, Mark, Cradle, etc. But they get also an access to the material solutions with what has been developed by Extreme Engineering, and so and also to some virtual manufacturing solutions with Simifact. And so all of these different products are going to be used in collaborations to develop a new component, and this is what I am going to explain you today. So Hexagon in general is active in in a large number of different markets. So of course automotive are key for us, but it's not only that, it's also aerospace, it's electronics, it's highway applications, it's energy applications, it's marines. So Hexagon is a bit everywhere. Every component that you are using, your car that you are driving, the plane that you are taking to go to Napoli, for instance, Hexagon is part of it in the development of the component of this device. So the applications that we are going to look at today is a mirror application. So it's directly an automotive applications, and okay, it's an external component. But as you can see here on this slide, Hexagon is going to act at different level. And for instance, we have a lot of initiative at the level of the battery. Perhaps that Alexi, that is here today, will speak about that during the multi-physics workshop. We have a lot of activity on the level of the battery, but also at the level of the electric motors or the body structure, for instance. But let's focus on the mirror applications. And so what we are going to do in these presentations is to create a digital twin of this mirror. So what is the case study that we would like to look at? So we have a mirror applications, and you have to imagine that you are a CAD designer or a designer in an automotive company, and you inherit from your previous colleagues from a mirror, but you cannot find anymore the CAD model of this mirror, and you need to restart the productions, or you need to improve this original design. Okay, so but you have no data basically. You are starting from nowhere, except that you have the real part sitting on your desk. So what can you do? You can take different tools of Hexagon to capture the real world data, to move to the questions about, okay, how could I remanufacture, reproduce this original design? How can I optimize my manufacturing process? How can I optimize my part to reach better performance? And how can I ensure a good quality of the manufacturing process? Hexagon is going to offer a complete portfolio to support that. Starting from the right, top right, we are going to have first a study at the level of the design. Get a first design from the existing component, validate this design, improve the design, prepare the manufacturing. So this can be done by using the tools that you are going to have in design and engineering. Then you are going to move at the step of the manufacturing. So which manufacturing process do you want to use to to produce this component. Do you want to look to additive manufacturing? Do you want to look to more traditional manufacturing process like injection molding? So these are questions that you need to answer. And when you have to answer these questions, you are going to be able to move to the productions. And so when you are going to produce the part, you will have also to inspect the quality. Quality is key at the date of today. If you want to have a sustainable process, you don't want to lose material. You don't want to have to push component that you have produced to the trash because the quality is not there. So you would like to have the part that is as good as possible, as close as possible to the original design, with a good quality, with a good lifetime. And so all this will require some specific quality inspections that you are going to be able to do with various tools of Hexagon. And as you are going to collect a lot of data, you need also to find information to manage this data, to analyze this data about the quality of the part that you are producing. And so the last step of reporting is definitively important. So we are going to go through these different steps in these presentations to explain you where Hexagon can help you at this different level. So, part optimizations using the power of one. So here you have a list of all the products, software and hardware of Hexagon Manufacturing Intelligence that has been used to solve this problem. So we are going to start by a first step that will be called reverse engineering, where we are going to combine metrology device with some software in order to reconstruct the original data. Then we are going to move to the simulations of the part to evaluate how to manufacture the part, what is the best process, but also what will be the performance of this part as it is manufactured. This will involve Apex, Digimat, Mark, Cradle, and also VZ for the production of the mold. And then we are going to produce the part, and we would like to do shop floor inspections. We would like to know the quality of the part in terms of size, in terms of defect that you could see at the external surface, but also inside the part. And it is there that we are going to have CT scan that will be used and various type of scanning system with also the support of volume graphics to analyze this data in order to give to the engineer responsible of the quality a good information on the quality of the part as it is produced. And we will arrive at the final stage when we are going to analyze this quality information that we have collected, and we are going to store that in the specific metrology reporting tool. So let's go step by step and a bit more into the detail. So the first step is to do this reverse engineering. And for that we are going to use some scanning system using hardware solutions of Hexagon. So we are going to combine hardware, absolute arm with absolute scanner, and VZ reverse software. What will be the value for the customers? First of all, this absolute arm and this absolute scanner is a portable and ease of use solutions. So you can bring that at your office, you can bring that on the manufacturing side. You can really scan the part where the part is existing. You are going to be able also to recreate a model, a cloud of points that will represent the part and that you will be able to use to recreate the final CAD. So, in terms of ROI for the customers, it's the faster go-to-market for productions of legacy part, because you will be able to reconstruct very quickly the CAD corresponding to your part, and you are going to be able to start to work on this CAD to improve the design. Here you can see the pictures or the way in which the tool of VZ is going to reconstruct the geometry, the CAD, from the cloud of point that has been measured with the absolute arm and absolute scanner. So for the customers, you will get out of that a direct CAD model with an automatic mesh creations, with some cleaning and smoothing to get a geometry that is as clean as possible to move to the next step. So quick and accurate creation of CAD. Faster to create new digital model. And so for the user, it will save a lot of time by following this path, instead of taking his pen and try to redraw from scratch, from a blank space, from a white page, the CAD of the mirror. So here at this stage, we have used absolute arm, absolute scanner with the VZ reverse engineering to get the CAD of the mirror. So the next step is to think about the manufacturing. Know that we have a CAD. How are we going to manufacture this component? What should we do to get the good representations, the good manufacturing of this component? So here we are going to evaluate two different types of solutions. The first one is the 3D printing of this component, and the second one is the injection molding for the same component. If we need to, if we have to do such a type of 3D printing process, we need something that will be able to sustain, to fix the part inside the printer chamber. And so here we are going to do is to optimize the jig that will be used to fix the part. So to do that, instead of to use a classical process that could be quite time-consuming to design the jig, we are going to use the Apex generative design that will optimize the jig in order to use less material, but with the same functionality that a more complex jig. And Apex generative design will allow us to get at this point in a faster way. So the value for the customers is that the jig that you are going to design will be lightweight, so you are going to use less material. It will be easier to manipulate by the engineers or by the technicians, so more efficient. It's a design that is tailored for additive manufacturing, so it's really optimized by knowing the constraint of the additive manufacturing process. And so in terms of ROI, we have a very good example here because BMW is using such a type of solutions to design their jig. These solutions allow them to get 72% lighter solutions than what they have used before, 58% saving in cost per fixture, and 92% decrease of lead time. So they are going to save time and money through these solutions by getting in a faster way the right jig for their final applications. So this is what we have done here. And so here normally we should see the video that will show you the environment inside Apex generative design. And so the first thing that we are going to do here is define a project inside Nexus to keep traceability of what is done by the engineer. This will allow the engineers to share his project later with his colleagues through the cloud applications that we have on Nexus. And so here he's going to work on this jig. So he starts from an original geometry, and then a complete process of optimizations will be applied on this design in order to lead to the final shape. You can see here the transformations from the original design to the final design that will reach the KPI that has been defined by the engineer in terms of volume, of weight, etc. You have a summary that is given here, and the result of this project will be uploaded in the cloud in order that you can share it with your colleague inside the company. So here you can see a first integration of the Nexus solutions inside a desktop applications like Apex Generative Design. I will have the chance later this afternoon to present you more in details Nexus and what is the vision and the mission of Nexus, and so you will better understand what you just see right now. This was for the additive manufacturing at the level of the jig. We are going to speak about the additive manufacturing of the part more in details in the coming slides, but what we wanted to highlight also is that it's one solution to use additive manufacturing to produce this mirror, but we could use also the injection molding manufacturing process. In this case, you are not going to use a non-reinforced plastic, you are going to use a reinforced plastic to have a good strength to impact, to have a good strength to shock, to have a good vibration behavior also. It's a part that is sitting there on the side of your car. If you go on a complex road, on a not nice road, it will vibrate a lot. You don't want to hear some noise of it, so you need to have something that has a good strength and that is able to damp vibration. So Plastic could be a good usage of this, but you need to have some fibers inside to reinforce the original plastic material. And so solutions like Digimat will help you to design that and to understand what are the benefits of adding fibers in your plastic for the final performance of the part. And so we are going to be able to couple here the effect of the manufacturing process on the fiber orientations that you have in the plastic on the final deformations of the component. So the solutions will combine different products from Hexagon, Digimat, Mark. Inside Digimat you have a Mordex 3D OEM version, so you can directly do the injection simulations inside Digimat if you want. And in terms of ROI, what we can demonstrate to you is that you are going to save a lot of time in the evaluations of the performance of your design. You are going to be able to optimize the gate positions to get the right fiber orientations to reach the right level of performance. But then, if we come back to the additive manufacturing process, you are going to have other type of challenge for the manufacturing. And one of the challenges is to say, okay, let's assume that we would like to use the fuse deposition modeling. Fuse deposition modeling means that you are going to have a filament of material that will be extruded from the head of the printer, and the head of the printer has to follow a given path to produce the part. If you do so, you have to first characterize correctly the material informations, because the behavior of the material in terms of thermal behavior and mechanical behavior will be very important to understand if the part is going to deform, what will be the exact shape of the part at the end, because during the cooling, the plastic is going to see its volume change, is going to see some residual stress building inside the plastic material, and so you can have some deformations that happen. And therefore, you have to think about all of that, and you have to integrate in this the effect of the tool path. So what will be the path of the head of the printers to produce this component? So the goal for us is to investigate the bar distortions, the temperature, the residual stress, and the warpage as function of the tool path that you are going to use, and to be able to optimize the tool path, but also the geometry of the mirror to compensate proactively any type of warpage that you could observe during the 3D printing. So here you can see these different type of results. So you have here the evolutions of the deflections during the 3D printing. You have the warpage indicator that will give you the indications where the deformations of the part is the biggest. You can see also the temperature. As function of the type of material that you are going to use, sometimes you could be interested to see the level of crystallinity that you are going to see during the 3D printing process. Temperature will have a very strong effect on the level of crystallinity, and therefore it's important to take that into account. You have also the residual stresses that can be obtained out of it. So we have considered here two different toolpaths that will lead to two different levels of deformations. We can look also at some specificity, some small device, specific feature of this mirror, like the clips that will be used to fix the mirror on the rest of the body of the car. And so you have this component is going to be produced also by 3D printing, and it will have different stiffness as function of the directions that will be used for the 3D printing. And so this is what we are analyzing on this slide. We are going to consider two different toolpaths, and as function of the toolpaths, we are going to have two different mechanical response of this small system here. So if we look at it, we are going to see that for the toolpath number one is the one that will bring the lower level of force for a given deformations applied on this component. And if we select the second toolpath, we are going to see that we are improving a lot the stiffness of this component and the strength also, because the maximum force that can be supported by this component produced with the second toolpath is much more efficient. Okay, so we can see that with the toolpath number one, we have a displacement of failure of 2.3 millimeters, while with the toolpath number two, we have 3.5 millimeters for the displacement at failure. So definitively, the toolpath number two seems to be more relevant for final applications, as this part has to accept some deformations when you are going to clip the mirror on the rest of the assembly. Now let's go back to the injection molding process. When you simulate the injection molding process, one important step if you want to capture completely the manufacturing process is to look at the mold. Because it's good to have just design of the part to be able to optimize the gate positions, but you have also to build a mold around it that will allow you to get the right shape of the part and the right shape of the part, basically. So for that, we are going to use the solutions that we have inside Hexagon that is called VZ, that will allow you to design completely the mold and to study all the effect of the cooling of the mold, of the injection point positions in the mold, on the overall general geometry of the mold, on the final quality of the part. Okay? By using such a solutions, you are going to see a time saving for the entire project estimated at around 45%. You have to keep in mind that produce a mold is something that is very, very expensive. It can cost several hundreds of thousands of euros to produce mold. And so it's a step that you don't want to have to reproduce too many times. You would like to get right at the first time the mold to produce your part because it's a very expensive and costly process. And so inside VZ, we are going to be able to design the mold, to simulate the performance of the mold, and to investigate the efficiency of the mold to produce correctly the part, basically. So the overall gain for the customers will be to have a faster design cycle, to improve the design, to have an insight into crucial design parameters, and it can lead to 50% of cost saving in the design of the mold. Then let's consider that we have now the mold that is ready to be used, that we are happy, that we are convinced by the simulations about the quality of the part that will be produced by using this mold. The next step for us is to move to the manufacturing and to check first the quality of the mold as it is manufactured, before to speak about the quality of the part coming out of the mold. And so here we are going to use some solutions from Hexagon Manufacturing Intelligence that are called Tiger and PCDMIS, that will allow you to evaluate the quality of the geometry of the mold as it is produced. This can be done at the shop floor and will allow you to measure exactly the dimension of the mold and verify that these dimensions corresponds to what you are expecting from what you have optimized inside VC. So it will allow you a digitalization of the measurement result, a quality control close to the manufacturing line. And so from these informations, you will be first able to, for the general geometry, to evaluate if the mold is correct or not for your applications. But it's not enough. And so you need to go a little bit more into the detail, and it's what we are going to do with the solutions called VID, that will allow you to do a visual analysis of the defect. And so here we are going to scan the surface of the mold to identify, by using some artificial intelligence technique, any type of defect that you could have at the surface of the mold. This will allow you to ensure that the surface of your final mirror will be smooth without any initial crack or initial defect that could lead to failure later during the usage of the applications. So it's a fast and accurate solutions to check the quality of the part as it is produced. It will avoid any complaint and reduce rework on the mold design and the mold manufacturing. It will increase production speed because you will be able to save time by identifying the defect and taking some corrective actions faster in the process. So here we are going to have a short video that will show how is working these visual detections solutions to inspect the surface quality. So there is many different types of defects that can be identified by the artificial intelligence solution that has been implemented in this tool. And so you are going to take a large number of pictures of your device, And from these pictures, this picture will be analyzed by these artificial intelligence solutions to identify and report all type of defects that can be observed at the surface of the part. So it's used by customers in many different type of markets. So we have seen some electronics applications, but we have also, of course also some medical applications, for instance, that can be checked by this system. And so this system can be implemented directly on the production line in order to collect image from different parts that are manufactured. And this will lead to a large amount of data that need to be analyzed and analyzed in an efficient way to be able to get an overall assessment of the quality of the productions. And you will see that Hexagon has a tool to help in this statistical analysis of this type of measurement that are performed on the line that is called QDAS. We'll speak about that a bit later. So the next step is we move from the mold to the part that is directly produced by using this mold. And so here we are coming back to the mirror as it is manufactured. And the first thing that we would like to check by using the absolute arm and the AS1 scanner is to check the quality of the part in terms of shape and dimensions. So does this part has the right dimensions when it is extracted from the mold? This is the question that we would like to answer by using these two tools. And so we are going to scan the material, we are going to get the external surface, and this external surface that we are going to be we are going to be able to compare it with the CAD of the mirror that we have optimized, and we'll be able to check if the part as it is manufactured corresponds to the part as it has been designed. It is here that we are going to create the connections between the real world and the virtual world. But it's not enough, because if you just look at the external surface, you are going to have an information about the general size, but you would like to also know what is happening inside the component. So have you the right fiber orientations, the right fiber orientations in the right positions? Have you any type of porosity inside the components? So all these type of things can be investigated by using CT scan, and it's what we are going to do here. Of course, CT scan will give you a large amount of image that you need to analyze and that you need to combine to rebuild the part in the virtual world, and this will be done with VG Studio Max. That will allow you to rebuild this real component in the virtual world and to be able to analyze fiber orientations, porosity defect, some dimensions also, in order to better understand, okay, does my part as it is manufactured corresponds to what I have obtained by my simulations? Do I have a correlation between the fiber orientations assumed in my design phase versus what I am observing in the real on the real component? So, for instance, here you can see some porosity that are measured by using volume graphics, and so you can see the volume of this porosity. So the absolute value does not speak too much, but you could also get a volume fractions, for instance, from volume graphics that will tell you where you have the biggest area with porosity, and you can then assess that, bring that back inside your simulations environment to evaluate the impact of this porosity on the final performance of the part. I was mentioning a bit before QDAS, because by doing all this metrology effort to assess the quality of the part that you are manufacturing, controlling the mold, controlling the part obtained at the end of the manufacturing process, you are going to collect a lot of information on the quality of the part that you are producing. And all these information that can be collected directly on the production line, you need to be able to analyze it and to extract some overall information about it. What is the quality? What is the number of parts that show some defect that does not allow to use this part on their final applications, that we should just push to the trash? And so all this type of analysis, you are going to be able to do it in QDAS. So QDAS will allow you to recollect all these informations. And this is the goal of the tool that we call metrology reporting that has been implemented in Nexus, is to have one single area, one single place where you can find all the informations about about the quality of the part that you have produced and the status on the production line. And so this metrology reporting tools is going to offer a cloud-based solutions to store all these informations and to make it available to all the stakeholders inside the company that need to have access to these informations to validate the quality of the component. So it will allow you to do quicker decisions, to do less mistake because you are sharing better the informations between the different collaborators, and to optimize the manufacturing and also the inspection process if you discover, thanks to these tools, that some important points are not checked in terms of quality. So thank you very much for your attention. If you have any questions, it will be my pleasure to answer them.